Good afternoon, everybody. Yeah, actually, I have the opportunity to talk today about what actually is combustion and why is it absolutely of paramount importance to be absent in actually heat not burn products. Just wanted to start with a slide. This is scientific data that we've actually published. And what it demonstrates that is if you can design a product that reduces the level of harmful and potentially harmful constituents significantly, it leads to a significant reduction in the toxicity of the aerosol. And we're going to go through the next few slides just to take a look at, in fact, compared to a cigarette where we have self-sustaining combustion processes, if you can design products that heat and eliminate combustion, in fact, you can reduce the quantity, the level of harmful and potentially harmful constituents. So what is combustion? So combustion is a rapid oxidative process between a fuel, so in this case if we take tobacco, and an oxidizer. And so an oxidizer is actually air, the actual oxygen in air. Now you need to initiate the reaction, so this is usually if an adult smoker has an actual match or a lighter, they basically set the combustion process in motion. And from it you generate heat. So heat and actually light. And so this is what people see, if you can actually feel. And also you get smoke and ash to it. It has key characteristics. So the key characteristic of a combustion reaction is principally that it's an exothermic reaction. So it generates heat. That heat you can actually feel. I think I mentioned it yesterday. If you see somebody smoke a cigarette in the evening time, when they draw air through the actual tip of the product, you can actually see it glow. So it comes out with it. It occurs at high temperatures. We're going to take a look at that next. And there are certain chemical compounds that you can actually look at to actually take and gauge, in addition to temperature measurements, if combustion reactions have actually taken place or not. If we take a look at the actual temperature scale, so if you take a piece of biomass like tobacco and you start to warm it up in air, a number of thermal processes happen. So as you go above 100 degrees C, you start to dry the actual sample out. As you go from 100 up to 200, 250, you start to evaporate chemical compounds that are naturally present. So nicotine is naturally present in tobacco, and it will come out of tobacco around about and above 150 up to about 220, 230 degrees C. As you continue to heat, you start to get thermal degradation reactions. So around the 200 to 300 degrees C temperature range, you get mild thermal breakdown. As you go higher in temperature, you start to go into pyrolysis reactions. And when you heat up in air, in the presence of air, and you get above 400 degrees C, you get the rapid oxidative reaction of the actual material itself. So this is when combustion actually sets in. And as you heat up, and as more oxygen is available, the fuel is now consumed, and you start a self-sustaining combustion process. If you higher up in temperature again, you can get into flaming actual temperatures. The two examples that I have on the slide are the flameless form of combustion. This is called smoldering combustion. This is, in fact, what a cigarette does. And then you have also flames. I think everybody's familiar. If you start a fire, you actually see flames. And the temperature of a flame is actually very, very high. So it's about 1500 degrees C. The slide I used yesterday. So when a smoker initiates the self-sustaining combustion reaction by actually taking a lighter to the tobacco being the actual fuel, the temperature at the tip is around 600 degrees C. And as mentioned just a minute ago, when you bring air and you feed that combustion reaction, the temperature actually rises. So every time a smoker would actually pull air through the actual product, the temperature rises. And again, you can see this very clearly at nighttime. That thermal energy, all of that thermal energy goes and can break down, in fact does break down the tobacco components that are actually in an actual cigarette. And it leads to the formation of a smoke aerosol that's very, very, very complex. There's over about 6,000 chemical compounds in there. And several of those chemical compounds have been identified or have been classified by public health authorities as the main cause or the likely cause of actually smoking-related diseases. Very quickly, so scientific studies have shown that if you heat tobacco to increasing temperatures, you increase the levels of harmful and potentially harmful constituents. So this is some research work that I did a little while ago, and we published in 2007. It's looking at a class of compounds that are called polycyclic aromatic hydrocarbons. And it shows that as you go up in temperature, the yield of these chemical compounds increase. So you can imagine if you can decrease the temperature at which tobacco is heated to, then in fact you will decrease these types of levels of harmful, potentially harmful chemicals. And this is the underlying principle with which we develop our heat not burn platforms. So this is our heated tobacco platform. I referred to it yesterday. Hope you had the opportunity to take a look at it at the stand that we had. And the underlying principle here is that if you use electronics to control precisely the temperature to which tobacco is heated, then in fact you can deliver nicotine, you can deliver flavor, and you can have significant reductions in the levels of harmful and potentially harmful constituents. So if we take a look at the actual temperature, so what does the temperature of the tobacco see? And as I mentioned yesterday, the blade, the actual heater that we use has two roles. So it provides the energy to the system, but it also monitors continuously the actual temperature of the system. And we place thermocouples at different distances radially from the blade. So in our product, the tobacco is heated from the inside out. So in fact, if you put a thermocouple on the blade, and you put it at different distances, so we put it at 0.2 millimeters, 0.5 millimeters, all the way out, you see that as you move away from the blade, you move away from the source of heat and energy, in fact, you get significantly reductions in the actual temperature that the tobacco is heated at. And you can see here, if you measure the temperature of the tobacco just off the blade, so 0.2 millimeters, this is equivalent to the thickness of the actual cast leaf sheet. You see that the average temperature that we record at the very end, towards the end of the 6-minute heating profile, is about 250 degrees Celsius. If you take a look at the bulk of the tobacco, that's further away. In fact, most of the tobacco is somewhere in the region of 200 degrees C and below temperature. So what we have here is that we don't have a consumption of the tobacco. We don't form ash. The aerosol that's generated is actually not smoke. And if you take a look at the tobacco stick, which is a multi-component that has tobacco in it, you'll see that it remains intact. It hasn't been consumed. It hasn't been degraded. There hasn't been ash actually formed to it. And one other thing I should point out, and this is a very indication, again, if I get the laser pointer. There we go. As you draw air through the system, you get a negative decrease in temperature. So I mentioned with a cigarette, in fact, you see it go up. So it goes from about 600 degrees C to above 850 degrees C. That's oxygen fueling that combustion process. Because we don't have combustion in the system, and because it's the heater that provides the energy to the system, when you draw air through it, in fact, it goes down. So every time you take air through the system, as seen here, you get negative decrease. So again, a very clear indication, in fact, that you don't have a combustion process in place. So we can go and look at markers of combustion. So as mentioned, you need an exothermic, self-sustaining process. Now, if we take away the energy, we take away the source of the heat, and we turn the heater off, if we had a combustion reaction, self-sustaining combustion reaction, the temperature would either stay the same or go up as we draw air through it. And what we see is the complete opposite. If we turn off the heater during the run and we take air through the system, so again, we give oxidizing into it, the temperature goes actually down. And because the heater's off, there is no recovery of the temperature system. So in fact, as you bring air through again, it will just go down and down and down. And we did it in one case where you take puffs under the Health Canada regime. If you just turn the heater on and you let it heat up, so you actually you let it heat up to the temperature, and you actually then turn it off and take a puff, again we see exactly the same thing. It's very endothermic. So in fact, the system needs energy. If you take that source of energy away, the actual thing itself actually turns off. So very, very different to what you see in combustion reactions. If you take a look at operating the system in nitrogen, so in the absence of any oxidizer, and you take a look at the chemical marker, so actually the oxides of nitrogen are very unambiguous markers. So you see actually very, very similar chemistry. So again, if you operate the system in the absence of oxygen at all, you get very, very similar actual chemistry of it. Again, indicating that there are no combustion reactions actually taking place. So we take a look at aerosol. So what is an actual aerosol? So an aerosol is a suspension of liquid and or solid particles or droplets suspended in a gas, and this is usually air. And they're classical examples. So if you looked out your window this morning and you saw the cloud, so cloud is an actual aerosol. The smoke generated from a burning cigarette is a smoke aerosol. And I'll just go in and show you the actual difference. So scientifically, smoke is an aerosol, and it's generated when organic matter undergoes either combustion processes or high temperature pyrolysis processes. Now, not all aerosols are smoke, as actually shown here. So if we were to start a campfire, we would have combustion, we would actually smoke generation to it. Again, the classical example of a self-sustaining combustion process is a lit cigarette to it. If we take a look at a humidifier, where it humidifies and generates a water vapor, that is not smoke. And the same thing if we were trying to boil pasta, or we're trying to heat actual water. The water is heated, it evaporates, it condenses above, and in fact this is not actual smoke. So we're very, very different scientifically between what aerosols are, what smoke aerosols are. If we take a look at the chemical composition, we see between a combusting, self-sustaining combustion process, which we have in a cigarette, and we compare it to a heat not burn product that doesn't go into a combustion mode, you see significant difference in the chemical composition of the actual aerosol. And you see here on the right-hand side, even visually, you can see very, very, very differences. And again, I think for anybody who had the opportunity, we had an actual demonstration machine outside showing you again the actual differences that you could even see yourself from it. The aerosol, because we heat and we don't burn, is actually mostly water vapor to it. One of the other products of combustion processes is actually solid carbonaceous particles. So you can take a look at the aerosol of your heated tobacco product, and you can compare it to what you get if you were to burn and combust the actual tobacco. And here on the right-hand side, you have an actual blank. If you look very, very closely at it, you can see a very small number of particles. And if you hit them with an X-ray, you can get the chemical composition. So if you take a look at it, these are from the apparatus. So if they're usually iron containing. So in fact, when you put two joints together, you always make a very small amount of particles. If you look at the tobacco heating system 2.2 aerosol, you see exactly the same type of apparatus generated particles. And if you take a look at what you get from a combustible product, in this case an actual 304F reference cigarette, you see there are a number of carbonaceous solid particles. A clear indication that you have a combustion reaction, but also showing that in fact if you don't combust the tobacco, you don't generate solid particles. Now we've also shared our research, we've also presented our research. We shared it with a number of third-party experts in the field of combustion. In fact, they've looked at the data and they've opined upon it. So they've either looked at the results that we have, they've either conducted their own experiments and confirmed, in fact, that under the controlled heating of our tobacco heating system, there is no combustion. In fact, the aerosol that's generated is not smoke. Actually, if anybody's interested, they can go on to pmiscience.com and you'll be able to see the executive summaries of these combustion experts and where they are. Now, just back again. So if you don't burn tobacco, but you controlled heat it, you can significantly decrease the level of potentially harmful constituents. And depending on which class of chemical compounds you actually look at or what regulatory authority you see across the board, you have significant reductions. I think it was mentioned yesterday that by heating and not burning, in fact, you have a significant cliff. It goes over a cliff and you have significant levels of actual reduction. To summarize, we have a set of robust scientific experiments that confirm that, again, if you can control the actual heating, control the temperature with tobacco is heated to, you can, in fact, eliminate any self-sustaining combustion processes. This has been validated by external experts in the field of combustion and thermolysis. And again, back to it again, and it should be for all heated tobacco products, eliminating combustion and controlling the overall temperature at which the tobacco is heated to gives you significant reductions. And this is the number that we found for our tobacco heating systems. We have an average 90 to 95% reduction compared to what you get in cigarette smoke. And the very last slide, and it's a very, very important thing, our overall step-by-step assessment program is not just built on a temperature measurement, it's not just built on the design of the actual product itself, or the aerosol chemistry, or the toxicity, or in fact the actual exposure that an adult smoker gets. It's the totality of it that has to be assessed, in addition of course to how consumers, how actual adult smokers perceive the product. And of course once the products are on the market, you must go out there and actually monitor how they're being used, etc. Thank you very much.